Alright guys, sorry about that. My computer did a stupid, so let's continue where we left off. So this is part 2 of the video. I'm still on page 20 looking at number 2. If you did not watch the first part, please go back and do so. But let's continue. So with number 2, alright, I'm going to do the number first and then I'll do the variable. So I'm going to break down the number first into a perfect square. So that'll be 2 and 9. So as of right now, I have, it's 9 by perfect square, I have 9 times 2. Now with 7, remember we want it so that if we multiplied a half to it or divide it by 2, however you want to see it, that it will come out evenly. And we know 7 divided by 2 is not a nice number, so we want to get the closest one possible. So we can break down x to the 7th into, if you just go one lower, x to the 6th, and you still have an x left over. So x to the 6th is a perfect square. This will then be times x to the 6th times x. Now when I rewrite this, I'm going to group the perfect squares together. So this will be the square root of 9, square root of x to the 6th, times square root of 2 times the square root of x. So this will be 3x to the 3rd, because if you divide 6 by 2, that's what you get. And you have square root of 2 and x left over. And that's simplified. So give number 3 a try on your own, and let's look at one like number 4. So number 4, be careful because it's not a square root anymore, it's a cube root, which means we're not looking for pairs of 2 or perfect squares, we're looking for pairs of 3 or sets of 3 or perfect cubes. All right. So if we start with, remember, a negative number with the odd index can become a negative number. So our answer is going to be negative. So with negative 8, we can break that down into 2 and 2, or 2 and 4. And then break this down into negative 2 and negative 2. If you look, we have 3. Plus, if you already knew that 8 was a perfect cube, you could have just gone ahead and wrote it like that. Then, r the 15th, r the 9th, both of those are divisible by 3, so we don't have to worry about it. So this would be negative 2 r to the whatever 15 divided by 3 is. So that's 5. And then t to the 9 divided by 3, or third. All right, give number 5 a shot on your own. And let's look at number 6. So number 6, we're dealing with a fourth. So we're looking for sets of 4. So first things first, I'm going to break down the 32. So I can break it down into 4 and 8. And we know that 8's a perfect cube, but it's not a perfect square. All right. Sorry, it's not a perfect fourth. So this will be 2 and 2, 2 and 4. Break it down again, 2 and 2. So if I'm looking at just my prime factor, so the bottom of my tree, I have a group of 4 with a singular 2 left over. So if I multiply 2 times 2 times 2, that gives me 16. So I can rewrite this as the 4th root of 16 times x to the 8th. We would just be dividing by 4. That is divisible by 4. So we can just keep this as x to the 8th. Y to the 9th. Again, you want to find the nearest multiple of 4 that's lower than 9. So with y to the 9th, the nearest multiple of 4 is 8. This would be y to the 8th with a singular y left over. So then we will multiply it times y to the 8th, 4th root, y, times, sorry, I ran out of room, guys, times y. And then same thing with z to the 7th. So z to the 7th, we want the nearest fourth, which would be z to the 4th. So we're left with 3 z's left over. So times the 4th root z to the 4th times 4th root of z. So all of our perfect fourths we're actually going to evaluate. So I'm going to highlight those. And then whatever's left over, that's what's going to remain under our radical. So 4th root of 16 is 2. 4th root of x to the 8, you just divide it by 4. So that would be x squared. 4th root of y to the 8th divided by 4, not 2, 4. That would be y squared. 4th root of z to the 4th, you just divide it by 4, so that would be z to the 1st, or just z. And then what we're left over with is a 4th root of y times z. So just to kind of recap what we already did, we're going to break the radicand into its two factors. One factor is the perfect square, cube, etc. So again, you can get it as best as you can, or if you can't find one off the top of your head, you can always just break it down to its prime factors and then just start grouping and multiplying back. All right. Take the root of the perfect number out of the radical sign. Leave the other non-perfect number inside the radical. You divide exponents by the index, and remainders stay inside the radical sign. And don't forget about anything absolute value. So what that means, don't forget about absolute value. All that means is that odd exponents or odd indexes, you can have a negative value or a negative root. Even index, there's no negative root. It would be imaginary. All right. So that's what it means by remembering the absolute value stuff. So just a couple of perfect cubes you may need to know. I recommend at least knowing up to 5 cubed, but you can go further than that. So with squares, you should know at least up to 15. Cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed 64, 5 cubed 5 cubed is 125. And if you want to go up further, 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. And then 10 cubed is 1,000. But in reality, you really just need to know these. If you know the other ones in the middle, that's great. Fourths, again, I recommend at least up to 5 and then possibly 10 to the 4th. So 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256, 5 to the 4th is 625. If you want to go further, 6 to the 4th is 1296. 7 to the 4th is 2401. 8 to the 4th is 4096. 9 to the 4th is 6561. 10 to the 4th is 10,000. And again, you really only need to know up till 5, and then also what 10 is. Perfect fifths, I would at least know up till, again, 5. So 1 to the 5th is 1, 2 to the 5th is 32, 3 to the 5th is Pretty sure it's, yep, 243. 4 to the 5th is 1024. And 5 to the 5th is 3125. If you want to go further, you can. So 6 to the 5th is 7776. 7 to the 5th is 16,807. 8 to the 5th is 32,768. 9 to the 5th is 59,049. 10 to the 5th is 100,000. Now, for the fifths, I would recommend at least up till the 3 to the 5th. If you want to go all the way up to 5, that's fine. You could always do up to 5 optionally, and you definitely need to know what 10 to the 5th is. And again, you're always welcome to use your calculator. It will do it for you, but it is a good idea to just do some off of memory because it will help. All right, so let's look at some examples. So let's look at letter A. So with letter A, if we just eyeball it, first off, it's a index of 3, so we're undoing a cube. So we're looking for perfect cubes. Well, 8's perfect cubed. X cubed, definitely a perfect cubed. Y is a multiple of 3, so it's also a perfect cube. So our answer will not include a radical. So the cube root of 8 is 2. If we divide 3 by 3, we get x to the first power. Divide 9 by 3, we get y to the third. If we look at letter B, so again, we're dealing with a perfect cube. Now, it is negative, but remember, since our index is odd, that means our answer will be negative at the end. So 40 is not a perfect cube, so we need to break it down into two numbers that are. Which, if you think about it, that would be 5 and 8. So 8's the perfect cubed. All right. If you take the cube root of 8, you get 2. So this will be 2 on the outside, and then you're left with the cube root of 5 on the inside. If you look at letter C. All right. So letter C, still dealing with the cube root. But 54 is not a perfect cube, so we need to break it down. Now we can break down 54 into 6 and 9. So since we can break it down to 6 and 9, we can probably go a little higher than that. So if we think about multiples of 9, that means possibly 27. So if I do 54 divided by 27, I get 2. So it goes in evenly. So I have 2 and 27, where 27 is a perfect cube. Now, x to the 4th. Again, you'll divide 4 by 3, whatever's left over, that's what you have. So if you think fraction-wise, 4 over 3, you can break that down to 3 over 3 plus 1 over 3. So this will become 1, and you're left over with that, or just the 1. So another way you can think about it is you can break down x to the 4th into its perfect cube, which is x cubed, times just a singular x. And then lastly, y to the 5th, same thing. Y to the 5th we can break down into a perfect cube, which is y cubed. And then we're left over with a y squared, because 3 plus 2 is 5. So that's my perfect cube. So for all of these, I'm going to find the cube roots. For 27, it's 3. X cubed, 3 divided by 3 is 1, so they're just x. Y cubed, same thing, it's just going to be 1, so y. This will be 3xy. And then whatever I have left over that's not a perfect cube is going back under the radical. So this will be 2xy squared. All right, last one that I'm going to do with y'all, and I'm going to leave the other 3 for you to try. So, D. Now be careful. We're now looking at a fifth root. So we're undoing perfect fifths. Now, 32, if we look back up here, 32 is in fact a perfect fifth. And the perfect fifth of 32 is 2. Now, x to the 11th, we want to break it down into 2 exponents where one of them is divisible by 5. Well, if we think about 2 numbers that add to 11 where one of them is divisible by 5, x 10 plus 1 comes to mind. So x to the 10th times x. Again, 10 is divisible by 5, so that works. That's our perfect fifth. Y to the 19th, same thing. We just need to find the number that's the closest to 19 that is divisible by 5. It has to be lower than 19. So you may be thinking 20, that doesn't work. You would have to use 15. So y to the 15th, and you have 4 y's left over. So if I take the cube root, that'll be x squared, because 10 divided by 5 is 2. And if you take the fifth root, it'll be y to the third, because 15 divided by 5 is 3. And of course, we're also going to write this outside the radical. What goes back under is what we have left over. So this will be 2x squared y cubed to the fifth root of x y to the fourth. All right, so that's it for this lesson. Your assignment for this lesson is just page 22. I would still give E, F, and G a try, and I will post those answers in the PDF version of the notes. All right, I hope this helps y'all. If you have any questions, feel free to email me or ask me on Monday.